Start that, and then screen share. Okay, so you were asking about what do I mean by collecting?
Yeah.
So in general, suppose I have some type T. Is that font big enough for you guys to see?
Yeah, for me.
Okay, I'll put it down here in the middle. Okay, so suppose I have some type T. Then I can define, let's say, the meaning of T. So to be all the programs P such that P is types by T. Okay, so that's one notion. Now notice that's a set, right? I used set to do that, right? So we might want to use something different. So if we use Wadler's comprehending monads idea, then we ought to be able to um, interpret the comprehension in terms of some monad. Right, so the list is a monad. So the question is, can we interpret this in this way? And what that would do is it would give us some ordering on that particular set, because the set has lost all information about multiplicity. It would lose that, but at least it would give us some ordering. Right? There might be you can consider multi-sets where P occurs more than once, right? So that's another monad. You could consider distributions where there's a likelihood that P satisfies T. So those are lots and lots of different notions of collections. And this is what we're talking about. We're not talking about collection in the sense of the term language. We're talking about collections that have to do with the relationship between the set of witness or the collection of witnesses of a type and the type, which is what I've expressed with this little equation here. Does that make sense?
Yes, 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 this makes sense. Thanks.
Okay, so then what Ladle is saying is whatever you use for this collection right here. Okay, so let's call that sub C. Okay. So Ladle is saying that you should be able to build those collections. You should be able to give a language for building those collections in terms of the language for building the programs themselves. All right. So for example, suppose I have the par operator. So I have P par Q. Okay. Then I should be able to build the meaning of P par Q in terms of the meaning, right? So it should be some gadget, say G, that I can apply to the meaning of P and the meaning of Q.
And this gadget is in Lambda application.
Well, yes, but it's application of what to what, right? Because yeah, so for par, this is actually going to be well spelled out, right? So it's going to be all the programs, say R, such that R is structurally equal. So I'll write it like this since I'm using ASCII. R is structurally equal to a P prime par Q prime, and P prime is in this guy here. Oops, that's weird. All right. And Q prime is in this one. Okay, does that make sense? So if we were doing the application one, so this is M applied to N, right? Then what we would like is that this is somehow some gadget G, or let's call it H, right? Because it's this different from the G above. That is in terms of the meaning of M and the meaning of N, right? Which is going to be, and we can just basically calculate it from above, right? So it's going to be all the programs are such that R is structurally equivalent to, so this is you know, an interesting one, an M prime applied to an N prime. So we can see the application, right? That means we can see into the structure of the program. And so just for grins, let me write it like this. Okay. All right. And M prime is in the meaning of M, and N prime is in the meaning of N. That make sense?
Yeah.
So go ahead.
I just wanted to ask, you said we know the structure of application, M prime applied to N prime.
We can see the syntactic. So what we're saying is we can see the syntactic form of the program.
Okay. I need to think about that more.
No, it just means we've got the syntax tree.
Oh, okay. Oh,
that's all it means.
I see. I see.
R is a syntax tree. It's enough for us to, right? That's it.
Oh, so when you say program, you mean the syntax tree, and this is from where we can say structurally equivalent, because we can compare these syntax trees.
Correct. Yeah.
Okay. Yeah. Thanks.
Right. So notice what we're doing, right? We're saying that the meanings of so I've done something funny, right? When you should have called it out, right? So it's really not P and Q. It's really T and U. Because up here, we were giving types. Okay. So what we've really done is we've lifted the par term constructor. So over here, this should be like that. That should be like that. And this should be that. And like that. And then same down here. So this will be T. This will be U. So now what we're really saying is that we can build these collections. So these kinds of collections here, in terms of their components. So here's the bigger collection, T par U, and we're building up that collection by looking at the collection T and the collection U. Right? So what we're really doing is lifting the term language up to a language that operates on collections. Does that make sense?
Yeah, and then in case of rolling, we have multi-set as a collection, right?
Multi-set is the natural collection because that's what par is. But I've already given the language for par. It's right here. It's that line where my cursor is. But we're not collecting it as a multi-set. We're collecting it as a set. So again, the point is that the way we collect the terms that satisfy a type is independent of the term formation. There are two monads. One is the collection for collecting things that satisfy a type. And the other is the monad that is associated with the language for the programs. There are two monads. There's a monad for the language and a monad for the collection. And the reason it's called ladle is because so let's say, since we've called the collection C, right, and we've called the monad for the let's give the monad for the language a name. It's kind of tough because we're restricted to ASCII, and we've already used a T for type. I would use L, but I want to use L for something else. Tricky. Used M. We've already used P. Okay, I'll just use L, and I'll use something else for the other thing. Okay, so notice that what we're doing is we're this function here goes from types over to collections of programs. So that's L. But it's a little bit more complicated because what it's really doing is it's talking about operations on these types. So what are those operations? Well, it's actually L of T, right? So we're lifting the language constructors to become type constructors. So L of T, right? And what we want it to do is to turn that into L of C. And what we want that to do is to become C of L, right? That's what's on the right-hand side of this collection, of this equation. These are C's, and what lives inside the C's? Well, program terms, right? That's what these R's are, right? So we're making a collection of programs, that's C of L. And where do we get them from? Well, we get them from program constructors over the collections, because each T and U are actually collections. right? That's what we set up here. Each T and U is a collection, right? So that's the C part. And then we build operations over those collections using the operators from the language. That's the L part. So this is a distributive law. It goes from L of C to C of L. That's why ladle is called ladle. Logic as a distributive law. So we're actually interpreting the logical operators, which are the type constructors, as a distributive law. And you actually get a classification. You get a whatever this collection supports. So if the collection is set, then we have a bunch of operations that are independent of the language constructors, right? So you have negation, right? So I can take set complement, right? That's that thing. And I have union, right? So these become logical operators. So this is or, and that's not. And that comes just from the C part. Has nothing to do with the L part, right? Right? So we get the normal, the sort of base logical operations come from C. Then the spatial connectors, that's all the ones that derive from the program constructors, right? So in the case of lambda, I have application. In the case of pi or rho, I have par. So the spatial operations come from L, right? So that's whatever your language is supplying, your programming language is supplying. And then the modal operations, which we haven't talked about here. This has to do with the COM rule, right? Or the beta reduction, right? So the modal operations come from the rewrite rules. So if you look at Hennessy-Milner logics, the modal operators come from the rewrite rules, right? So each of the different pieces of your type system or your logic come from the different components that are associated with the data given by the distributive law. Now, even though this is a very compelling idea and there's a lot of legs to it, there are problems. And the biggest problem is there are lots and lots of no-go theorems for certain kinds of Cs. So you can't get a distributive law if you if C is not very, very set-like. So if C is a list, this distributive law doesn't exist.
And this is directly connected to what base logical operations we get from C, right?
That's correct, right?
Okay.
You can't get, so here are some things that will work. So set, multi-set, we're pretty sure distribution works. But there are things that won't work. So in order to preserve the sort of spiritual side of this, but make it, so the intuitions are spot on, okay? But the categorical interpretation, this is too restrictive. So what Christian Williams has done is instead to look at sheaves over a theory. So what is the theory? Well, it turns out that the monad L corresponds to a Levere theory. So that's why I picked L as well. And what we're so what he does is he says, so sheaves over a theory is basically going to be some category to the theory op. So it's going to be to the op of the theory. Okay, so that's, and then he picks some topos for C. So the topos gives you your base logical operations. The spatial operations come because the sheaves lift the theory, basically through the logical operations. And then he's now working on the modal operations, but there's still a lot of work to be done there, because if you don't treat it as rewrites, then you lose lots of information. So that's an alternate approach that Christian Williams is using to give the categorical semantics for these intuitions that I've been sort of carrying around since 2007, 2006. But I mean, you can easily express it in set, right? You can, if you just use sets, then this whole construction is quite straightforward, which is why, sheaves where C is a topos is sort of the natural place to start. If we do the sheaves construction as sort of the default interpretation of these ideas, then it gives us more freedom. We're no longer stuck with the kind of restrictions that the distributive law requires. But in particular, what it does is it gives us we might be able to pick a different category. So a category that supports lists. So the one thing that I want to look at fairly aggressively is if you pick the category to be a categorical model of linear logic, which is the one that's really interesting. Lists, may have some interest, but linear logic is very interesting from a certain perspective. So if, for example, you pick some star autonomous category, then, and you do sheaves over the star autonomous category, then your base logical operations will come from linear logic. And the rest of this remains unchanged. And that has all kinds of nice properties about it. But this is sort of the, when I say collection, I'm talking about this thing here. How do you collect all the terms that satisfy a type? And that's a completely independent choice from how you built your programming language in the first place.
I see.
Right? But the reason this is practically interesting is how you collect the terms that satisfy a type is related to things like GitHub. Right? So GitHub holds a bunch of programming language examples. It holds a bunch of programs, right? This, in fact, what it holds is the syntax for a bunch of programs. And now suppose you wanted to search GitHub on the basis of program construction. So is this program a par, or is this program an application? Even better, does this program have the possibility of evolving to that program over there? So those are your query constructors, and these things are going to be the results. of your query constructors. So Ladle is a query language for GitHub. And now, if you stop and think, what is most likely going to replace GitHub if it is successful? Well, how about the blockchain that has smart contracts? Every smart contract is a program stored on a, global public storage mechanism, the blockchain. Now, if that were true, if that's what comes to pass, right, then there are going to be lots, and just like on GitHub, there are going to be lots and lots and lots of smart contracts. And you want to be able to find them. Now, do you want to find them the way we currently search GitHub, which is in terms of metadata, in terms of social connections, and that sort of thing? Right? That's not very efficient. It's not a particularly good use of the data. And in fact, if you think about it, code is sort of the dark matter of the internet, right? Because it's unsearchable. It's a data asset that is essentially unsearchable because we don't have a mechanism for searching on the basis of its structure and what it does. But Ladle, this approach provides a basis for searching these repositories of code assets on the basis of its structure and what it does. So that's one of the important practical applications.
Yeah, this searching, but by what it does is especially interesting.
Yes, yes. And people have long thought that that would be impossible because of the halting problem. But it turns out that there are wide classes of program evolution that are absolutely searchable.
And this is, in a sense, sounds like searching the proof. So we have part of the program with some hole that we know this hole is like a T, and we are searching all the possible P's that can go for this T, right?
That's exactly correct. That is exactly correct. So, so that's exactly right. And what that does is that gives you a, so I noticed that Theo is here. Theo might be interested in this. That gives you a visual language for writing down queries. So if you have a visual language for writing programs and you give to it the property of knocking a hole in your program, and you specify a type of program that can go into that hole, then you have a query. And you can now launch that query against a repository, such as GitHub or your smart contracting platform.
Yeah, that definitely makes me think, like in terms of, there's like Visual Studio auto-completion that kind of uses neural network, and it kind of can assist you when you're writing a program. Kind of makes it like almost if you miss a certain term, it kind of auto-fills it, like says you probably means this instead. So
That's right.
I'm thinking maybe there is like a way of building a program and just telling it, like almost giving it a satisfaction, like a set problem.
Yes,
I want this program to do exactly this. Like I want it to output this when I give it certain inputs.
yes. So now we come to the full vision, which I sketched out in 95. I was a research fellow at, or not fellow, but researcher at British Telecoms. I was a part of work I was doing for while I was doing my PhD research. And I sketched out the following idea. you have these repos, but they're distributed. So there isn't one repo. You have lots and lots of them up in the cloud. And you hit one, but they're all connected with each other. And then you hit one of them with your query, you know, so one of these things here, the T's and the U's combined in a particular way. And what it does is it says, okay, I don't have what you're looking for, but what I've got are programs that match up to a particular delta. Now I can go ask, you know, all of the repos that I know if they can fill in the delta. So how do we calculate the delta? Well, it turns out that there's an operation called residuation, which will calculate and it's related to linear logic, which is why I'm so focused on linear logic, which will calculate essentially what you're missing from your type in order to satisfy a particular spec. So it's very, very closely related to linear implication. So residuation and linear implication are closely connected. In this way, and you can recurse this process, right? So let's say they say, well, I don't have exactly your delta, but I have these things that fit in and give me a new delta, which is smaller. And in this way, you can assemble a program that no human being had ever written out of programs from the, you know, that have been written, right? That are in this network of repositories, right? So now you have an actual AI because it's actually writing code out of code pieces that have already been written. And then of course, once it's written that code, it can then store it in the repository. And there's a justification for storing it because at least there was one client that wanted that program. Does that make sense?
Yeah, totally.
So this is, go ahead.
And I mean, this is very different from what Theo mentioned. I mean, Microsoft is doing this, but they don't have the same starting point. They have like big data of all the programs, and they say, oh, in this case, other programmers usually are writing for loop here, but they don't have understanding like why this program is structured like that, right? They're just comparing with existing data. So
yeah, well, they do have the types, right? They have the you know, they have the method signatures. So
yeah, but they only have spatial operations. They don't have model operations at all.
That's correct. That's exactly right.
And then and they don't have this they don't think about that at all.
That's correct. That's correct.
Yeah.
So this is why we do this. And it's an absolute necessity if we're talking about building a giant global computer. Right? I mean, if we're really going to build this giant global computer that's running, you know, in a decentralized fashion across all these nodes, then this basic utility that I'm describing here is a must-have, because otherwise it becomes quickly too difficult, too large, too data intensive to handle. But this handles the data at that scale, right? Where by data, I'm talking about programs as assets, programs as data assets.
Yeah. And what you mentioned last time, we can destructure these programs and exactly know all of the pieces.
Correct. That's exactly right. At least structurally, you can know everything. Modally or operationally, you can know quite a bit, but the more you ask, the harder and harder it gets to answer the question until finally it takes more time than there is available in the universe to answer. But if you look at the way programs are actually written by humans, most humans, you know, they build these little cultures, and these are cultures of certain design patterns that they understand very, very well. And those design patterns sort of get them, 99% of their cases. And then outside of those 99% of those cases, they do, very, very difficult programming. So there's this sort of these culture around these design patterns is corresponds to fragments of these languages where you have some kind of decidability property. That's why they show up, is because people know how to reason about them, because they've intuited or been very explicit about certain properties that they're trying to hold all throughout their system. So you can now identify them and emulate them. And in fact, the whole point about the combinatorial investigation is that we can classify a big swath of these design patterns in terms of the underlying operations of a particular language. So in the case of the pi calculus, for example, Yoshida is able to classify like all the different fragments where fragmentation comes in terms of the basic operations of the language. So that's we can automate even that. We can talk about, okay, well, if you want this kind of expressive power, these are the combinators you want, and so this is what the decidability characteristics are for modal search. So we can get really, really crisp about exactly where the dividing line is for the operational side of the theory. And some people are even going to be okay with undecidable fragments, right? Because what they'll do is they'll put a time bound or some other kind of resource bound like gas on how long the search is it's okay to go, right? So for example, people for a very long time now, people have been searching different kinds of mathematical spaces, whether it's prime numbers or other kinds of things, where they know that the searches are they take forever, but they use bounded amounts of compute resources in order to go and run their experiments. So that's sort of computer science as an experimental science, or math as an experimental science. So this kind of behavior or phenomena is absolutely something that people have been doing for decades and will continue to do. And if they have if there are fragments that where the search is undecidable, it doesn't mean that all hope is lost. It just means that some searches may never come back, but there can be searches which are still fruitful. And if you have enough resources, you can go find the thing you're looking for. So even in that case, the halting problem doesn't necessarily get in our way. Does that make sense?
Yeah. And can we also have situations where we have multiple results?
Yeah, of course.
Yeah, of course.
Yeah. Absolutely. And so the other part of this, of course, has to do with so I've there's a natural parallelization, right? So part of if you my puppy wants to go out. If you give me a query that's like this, T par U, where then I could give to one server or one network, hey, go figure out what T is. And I could give to another network, hey, go figure out what U is. So the point is that you can parallelize a whole bunch of this once you have this compositional framework. And again, this is very much opposite of the way AI is currently being conducted, right? So what I imagine is this giant network of theorem provers or model checkers, depending on which approach you take, but let's say they're theorem provers. Then you want those theorem provers to be able to coordinate and collaborate. And that way you can do these searches in much lower time bounds. Does that make sense?
Yeah, I'm also thinking we can use this in games to generate graphics and in some specific way, because we have like types for our universe, right?
Absolutely.
Which we want to have in game. Yeah.
So I can give you a lot more specificity on that. There are a lot of algebras that are really good at geometry.
You mentioned
Clifford algebras are really good at geometry. The reason I have organized the ladle work at the level of generality, like I could have stopped at namespace logic and said, okay, that's it, I'm done. But the reason to go to this level of generality is because these things over here in the type land, which is your query language, they derive from the whatever domain language that you've given, the program land, right? And so the lambda calculus, its worldview is compute as function, right? And the pi calculus and the rho calculus, their worldview is compute as interaction. But there are other worldviews. So the Clifford algebras are compute as geometry. And so you can then use the ladle program to make a query language for the compute as geometry idea. And then you get geometric queries. So there are all kinds of things that you can calculate. Find me all the things which are rotations of this thing. Find me all the things which are translations of this thing. There are all kinds of very specific, real kinds of things that real questions that are interesting. Like, the example I used to give in earlier talks was find me all the wires running from the nose of the airplane to the midsection of the airplane that are likely to undergo a twist. Because when wires get twisted, then we know they can become crimped, and when they become crimped, then they can't pass the signal through. Right? So that's a practical question. We want to know about those things. And you can write that down in Clifford algebra, and you can turn it into a query using ladle. That query is impossible with the existing databases. You can't even write it down.
Interesting.
Yeah. So,
and just one question, if I may. This T and U theorem provers, they're really, they can be very general, right? We can use something that we have in Clifford algebra or Rolling, and we can use the same provers, right?
Yeah, that's the idea. That's the idea. Now, in general, you want to be able to substitute in special purpose things, right? So, for example, if T and U do, include a sub-language, which is the language of arithmetic, which is very common in programming languages, right? Then you want to be able to plug in SAT solvers and other kinds of things, for which we've had decades and decades of experience, giving, optimized solutions for it, right? So that's the other reason to do this thing compositionally, right? Because that way we can, compositionality means pluggability. So we can, for that subfragment, we just plug in, rather than do this general purpose semantics, we plug in the special purpose semantics, which is smart about, you know, that particular subdomain.
But we can translate between different specialized versions. As you have in your example, you can translate from Pi to Roland directly.
Correct. And in fact, you can check the correctness of the translations. That's the other thing, right?
Yeah.
Right. So we got this framework for checking the correctness of the translations.
Yeah, this is nice.
So that's the. I was going to show you some. We could talk about next week. We can talk about trace. So, I now have fairly high degree of confidence that the construction, the proof theory construction corresponds to a notion of trace. So I've been wanting to find the time to sit down and write out what that notion of trace is. Oh, here, a trace is a kind of operator on a category that gives you sort of a convergent recursion. So these are recursions that, you know, terminate. And so I'm almost certain that we can write down the ladle construction that sort of uses gas or flow or whatever you want to call it, the evaluation context, as a trace. It's a particular kind of trace construction, which I think will be of interest to the category theory community folks as well. So that's another piece of the puzzle, and it's quite pretty because there's a nice equational characterization. And, you know, just to tease people, the thing that I hypothesizing seems intuitively correct is the error correcting codes in approach to the getting Casper to be live. I think that also falls under the same rubric, that the bounds that they put in order to ensure liveness correspond to convergence with respect to a trace. So you know, there's a deep connection between these two things. So I'm hoping to spend more time and write out, do the first trace, and then that will give me the inspiration to write out the liveness stuff in terms of a trace. Anyway, I'm going to take a few minutes to walk the puppy before stand up. So thanks everyone for your time, and I apologize. These are kind of repeat ideas. You know, I've been talking about them a lot, but I think not very many people know these ideas, so I have to keep repeating them.
Oh yeah, thanks for repeating. This is so useful. Yeah.
I had an idea. I don't know if you're interested, but what if you could like write it down as you record the session, like in OneNote, for example, and at the same time, like it can be useful for newcomers to kind of go through your annotations and even search in them.
Yeah, it's so what we were doing was transcribing them. So we'll probably start transcribing them again. It's actually fairly easy to transcribe them. So
this is also.
Go ahead.
I mean, this can also be some work for us as a community to bring this thing together and, you know, try to make sense of all of it, right?
Yeah. So that would be great. That would be, you know, we can all support each other in this way, right? I'm sure lots of people have really much better ideas than I do. So I'm happy to transcribe their ideas as well. But let me jump off and get her out, and so I can do. All right, thanks guys. I really appreciate it.
Bye bye. Thanks.